You've got this drag curve, and it's a very specific shape for that specific shape of bullet. Anytime you start to change the design of the bullet, where you change the MEPLA diameter, which is like the flat open tip or like the flat tip on a plastic tip bullet, like the Hornady's.
Okay.
Or you put like a boat tail on it or a flat base. You start changing that, the actual shape of the drag curve, that shape changes.
All right, Vortex Nation, what's going on? We are here in the studio, and I got to admit that I think we've done now a couple hundred episodes, Mark, and I have never felt nervous before a podcast until right now.
I feel so good because now I know it's not just me.
Okay, because the brains across the table are, the people across the table are going to talk about some stuff that I wish I even knew how to like scratch the surface of, but you guys have really dug deep into these topics. You guys are from AB, and we have Chris Wienche across the table and Mitch Fitzpatrick. I got it out. Okay, bit of a tongue twister name. But yeah, Applied Ballistics crew here as part of helping us out with some of the initial training and run-throughs. By the time you're listening to this podcast, the Fury AB 5000, oh, wait, hold on. Fury HD 5000 AB. I think that's actually the proper nomenclature. Will have come out. There it is.
Talk about tongue twisters.
Yeah, a little bit. And so it has AB on board, which is a, kind of a ballistics solution. And it's more than just maybe your average ballistics calculator you might download or get on the internet or whatever. It really is this all-encompassing thing that there's things like custom drag curves, and there's then giving you all this data to ideally, for all of you long-range enthusiasts out there, or get you as accurate as possible downrange. And so you guys are taking into account, just this immense amount of variables that are happening upon your bullet as it goes through the air. It's pretty crazy stuff. But first off, we got to let them introduce themselves because we've heard that once you guys get talking, you can kind of just go right off. So we got to at least let everybody who's listening out there know who you are. We'll go alphabetical by first name. So Chris, we'll have you start.
Yeah, no problem. So basically, I kind of grew up, hunting and shooting in South Australia. And then after a while, kind of split from the air rifle, the little 177, into the little 22 rimfire as a kid, and then gradually got into long-range shooting in the mountains and hunting in the mountains there, and then ended up finding my way into the military. It's usually kind of natural progression at that point. Ended up doing some work over in the Middle East for a little while, and then streaming through to the sniper community after some time. Had a pretty extensive career in the sniper community for a good few years. Finished a bunch of different courses, some related to advanced sniping, others relating to just other generic things like combat signals or combat tracking, things like that. And then decided I wasn't really done with the Middle East and went back to contracting with the Australian government to Afghanistan, because I love the place so much.
This is also part of the reason I was nervous for this podcast, because I'm sitting directly across from this guy.
Because he's so cool.
Right, yeah. He's like very calm, cool, and collected, but I know what he's done in the past a little bit, just based on, anyway.
So I did that. Yeah, I did that for a few years, and that was really interesting. I got away from the long range stuff for a little while. A lot of more protection, close personal protection type stuff for those few years, and then went back to the sniping stream for another year and a half odd. And was fortunate enough that, my contract was coming towards an end with the military, and I decided that, maybe it's time to branch out and look at other options. Now, AB originally was, they were advertising for a mechanical engineer position, and I'm no mechanical engineer, by the way. Never done a day in college, right? But actually, I took that email, Brian's email, and I sent my CV out to Brian, and I said, hey, look, I'm no mechanical engineer, but here's my CV, here's my qualifications, here's some, pretty solid reference letters from some solid people, and maybe you've got a use for me. And we continued to have that discussion, and it led to where I am now. Yeah.
That's awesome. Super cool. All right. Well, appreciate you sharing that. And then Mitch, we'll have you introduce yourself too. And then we were saying, and we almost accidentally had a podcast before the podcast, because every person that I've heard thus far, when they're like, "Oh, wait till you get Mitch on the podcast," that guy knows a lot of stuff. Now, you just graduated from college, so I was trying to figure out. I actually, in my head, was picturing somebody, who looks like Einstein, and at least in their 70s with all this extensive knowledge they know.
Oh, somebody's really, really hyping me up.
It's just me in the background pulling strings, mate, setting the bar high so you have to bring it.
This is us just trying to make you nervous.
Yeah, obviously, yeah. So I just graduated from Michigan Tech, which actually isn't terribly far from here up in the Upper Peninsula.
Sure.
Went to school with a lot of people from Wisconsin, but I started working with Applied Ballistics. I'm trying to remember what year it was now. But I was like in my sophomore year of high school. My uncles have a pretty good sized farm in Michigan. I'm from Central Michigan. AB's based out of Michigan, and I had access to lots of land. And from a hunting perspective, we would see deer a long ways off, and we're like, "Oh, there's got to be a way we can shoot them further away than having to like get within a couple hundred yards or whatever." So that's what kind of first set me on the course of long range. Is I wanted to get better for long range hunting, and but as soon as I started looking into it a little bit, I came across some different types of shooting competitions that were taking place in Michigan, and the first one being like Palma or F-class competition.
Oh yeah, okay.
And so I drove up to Camp Grayling, there's a military base there. They don't hold matches there anymore, but they did at the time. And drove up there to like just kind of check it out. Me and my dad went up there and started kind of talking to some guys, asking some questions, just seeing what they were doing. And one of the guys is like, you gotta go down to the other end of the line here and talk to that guy. His name's Brian. He's a ballistician. He like works for Burger Bullets. And I'm like, oh, Burger Bullets, that's cool. So I went down and started asking him some questions, and pretty advanced, in-depth questions. I would guess for a 15-year-old, because I'd been researching it and trying to get into it for quite a while at that point. And so he gave me some good pointers, and I took a lot of information away from that day. But the way I really got into it was I didn't have the money to buy my own equipment, so I started, along with help obviously from my dad and uncles. They've got a farm, so we've got mills and lathes and equipment like that, and I started getting on CAD, and we just started building our own rifles. So started doing all of our own gunsmithing work. I drew up and made an action, and I was buying like flat top blank wood stocks and finishing them all out and doing all that, and they shot really well. I mean, we were getting half MOA results with some what we thought were pretty cheap parts, but parts we could buy. And I started shooting F-class competitions and was doing really well as a junior. I was in high school at the time, and I ended up the Michigan F-class team guys had me come on the team with them and start shooting. And Brian was the coach of that team, so that's where I got to work with Brian a little bit more. And one thing led to another, and Brian kind of recognized that I was very passionate and interested in long range shooting, and had already kind of taken it upon myself to figure out almost everything I needed to be pretty effective at it. I had bought his book. Actually, my uncle had bought his book, and I was reading it, and before I even really made the connection that it was his book. Nice. And one thing led to another, and he kind of offered me a position. I shouldn't say a position. Offered to let me kind of intern with Applied Ballistics, and here we are. It's like 7 years later. I think I was 15 when first met and started shooting. 16 when I really started traveling with the F-class teams. And everything just snowballed from there. We've been doing F-class and then ELR and all that good stuff.
Well, you're into F-class and ELR. So if you're like any of the other F-class and ELR guys I know, then you are pretty smart. So, yeah.
I guess I didn't go into that. So I got a degree in mechanical engineering with a minor in aerospace from Michigan Tech. And that was, so obviously I was already working for AB, kind of was already planning on going down that route, working with Brian, and Brian was, AB's actually changed a lot since I've been there. We were joking about it. I think besides Brian, there's only one other person that still works there from when I started. So even though I just started full time, I've kind of been there before
been
everyone
around
else.
The block.
Yeah.
Right? Seen everything.
Yeah. So, that kind of shaped that. I'm like, okay, this is what I want to go into. Kind of want to keep working with Applied Ballistics. So I went into mechanical because tech doesn't have a dedicated aerospace program. So I got the aerospace minor on the mechanical engineering degree, and
wow,
that's my background, kind of my introduction how I got into shooting and how I got to be sitting at the table here today.
Yeah.
Right on. So you guys basically are your like obsession, for lack of a better term, is just trying to figure out what is happening to a bullet in flight.
Yep.
Is that pretty much
Yeah,
accurate?
you could summarize it like that for sure, Jimmy. Yeah.
So that way-
external ballistics.
Yeah.
That
Okay.
would be the kind of the proper term for it. So
Is there such a thing as internal ballistics?
yeah, there is.
Yeah.
Yeah, that's and we kind of dabble in that a little bit. We haven't done too much, but that's more like load development and how does the burn rate of powders affect things.
Okay.
The vast majority of what we do is when the bullet leaves the muzzle.
Yeah.
How do we predict what's going to happen?
Okay. So a lot of people have probably by now, and hopefully if you listen to some of our podcasts, we talk about this stuff, right? A lot of people have gone in, and you get the fields to fill in on a ballistics calculator somewhere,
Yep.
and you fill in, if you're really into it, you got some kind of a chronograph or, Doppler setup or whatever,
Yep.
and you got your muzzle velocity and, the grain weight of your bullet, a few other factors, and you plug it in and stuff just gets spat out, right?
Yep.
It's all magic. Seemingly to people like us. And in a lot of the podcasts we've talked about in the past, we just literally have just said, you don't necessarily have to be like a rocket scientist, which essentially these guys almost are, or maybe just are straight up, to figure out this stuff because a lot of the work has been done for you. But this is the chance where we get to peel back the onion and we get to ask you guys about what is going on under the hood. And then also another big thing we want to talk about is some people might be familiar with, you've got G1 and G7 ballistic profiles,
Yep.
whereas you guys have taken it yet to the next step or maybe 2 steps beyond to these custom drag profiles and even personal profiles for people who are shooting, one specific type of bullet, even off of one specific lot of ammunition,
Yep.
and through their rifling and with their setup, their barrel length.
I was
going
going to say, we have all these variables that
Right.
affect the bullet, how it's what happens to it after it leaves the barrel, and like I was going to bring up that exact same thing because I'd never even thought about how the individual riflings from different barrels will affect a bullet differently.
Yep.
Yeah. So talk to us maybe first, and we'll kind of like graduate ourselves into the real complicated stuff, perhaps. But talk about us first, like what is happening under the hood as people are inputting data like muzzle velocity and the grain weight, and then you talk about different shapes of bullets. You got boat tails, and you got these flat bottom ones that look kind of like, I just always call it the bullet bomb from Mario Bros. But like. Yeah, stuff like that. What's happening under the hood?
There's so much happening under the hood.
Yeah.
Jimmy.
Okay, so I thought that was like a simple start, but it's probably just I just kicked the hornet's nest.
So I can speak to more so the solver itself, and there's a few different ways you can go about calculating ballistic solutions, but the way our solver works is a numeric style solver where it will run a point mass solving a solution, and what it's doing is it's basically time stepping the position of the bullet from the time it exits the muzzle to the time it reaches the target downrange. And so what it's doing is it's separating or incrementing the bullet's trajectory into very, very small increments all the way down range. And so as it time steps, it's basically asking the question, where is the bullet? What is it doing now? And it runs the equations of motion and it calculates the position of the bullet, and then it does it again for the next time step. And
if you had like 10 million cameras between your muzzle and the target, it's almost taking these individual snapshots.
Yeah, essentially.
The course.
Yeah.
And so what it's doing is it's solving those equations of motion for each time step as that bullet flies downrange. Now, as that bullet, gets to the target end, it's able to say, okay, this is the position of the bullet and this is what it's doing, and here's your firing solution. But there's so much more that needs to be input by the user on the user's end to get a good, accurate, solid firing solution. And I always kind of say to shooters, when it comes to ballistic calculation, it should just come down to a good, solid wind call. The shooter should just have to make a good solid wind call. Elevation, everything else, taking into account second order effects for, spin drift, aerodynamic jump, and vertical and horizontal Coriolis. That is all completely
talk about that stuff.
deterministic, right? And we should be able to calculate it out, and we can calculate it out as long as we give the ballistic solver the correct inputs. And so the way I kind of tie that back in is with the ballistic solver, it's kind of like a calculator on steroids, right? But ultimately, if you were to punch a problem into a calculator, just 10 times 10, and it busts out, 90 or something, right? You've got a kind of a general idea of what that calculator should spit out in terms of an answer. So at that point, you're like, well, this answer isn't quite right. What's going on here? So the first thing you go back is verify the inputs for your problem. And usually you find, okay, I punched in the wrong number. I went, 9 times 10 or whatever. And that's how I ended up where I was. My point in saying that is a ballistic calculator or a ballistic solver can be treated like a calculator in the sense that it's calculating your firing solution. All you need to do is give it the good solid inputs that it needs to give you the most accurate output. And that kind of ties back to GIGO, garbage in, garbage out. If you are fudging certain elements of your ballistic profile, like your muzzle velocity or your launch velocity, obviously your remaining velocity downrange and the subsequent drop that the bullet's going to experience is going to be a variable that, you're going to have to work to correct, as opposed to getting a good solid muzzle velocity from a chronograph, right? Now, ultimately, what the solver cares about is a few different things. It likes to know what the air density is because it needs to know how thick the air is that the bullet's flying through. It also needs to know what the local speed of sound is, and that goes into, in the background, what it's doing is it's looking at the bullet's coefficient of drag relative to Mach number. Okay. And the reason it's working on Mach number is because obviously the speed of sound changes relative to the local atmospheric conditions, right? Temperature being...
That's not obvious, by the way.
Okay. How is that, by the way? So we were discussing this, and because Katie came in from Kestrel, and she had mentioned that as well. That was something that we discussed, and then it hit me. I was thinking to myself, well, wait a minute. How does the Mach number, which is the speed of sound, the sound barrier, which is in and of itself, the sound barrier is baffling. So anyway, well, I'm sure we'll get into it. But it changes. So like if it was drier air at higher elevation, it's
mostly tied to temperature.
Yeah. Oh, it's mostly tied to temperature.
Yeah.
Oh, okay. So our Mach here in Wisconsin could be different in December than it is today. Or
the local speed of sound, the Mach number is always going to be the same, like relative, because Mach 1 is the speed of sound, right?
Okay.
So to standardize that, let's say that at mean sea level, your Mach number, or your speed of sound, Mach 1, or the speed of sound would be somewhere around 17 feet per second, right? Now that velocity, and I'm talking, that's the velocity of the bullet downrange.
Okay.
So if you were firing that bullet through less dense or more dense air, the velocity of that bullet is going to be somewhat different relative to the density of the air, and subsequently that'll affect the speed of sound.
Oh, okay.
But the reason we use Mach numbers is because the coefficients of drag and the shape of the drag curve is all tied to the relationship to the speed of sound. So it's all based on Mach number. That's why we can't just skip Mach and just use the velocity in feet per second or something like that.
So if Mach is a higher velocity, then it will change everything even before it gets close to the Mach number, right?
We're just using. So you need to know the Mach number to be able to accurately say what the drag is at that step in the time steps that he was talking about for the solution.
So it doesn't necessarily matter what the actual velocity Mach 1 is, because it's all relative to 1.
Yeah.
So you've got to can be hard for people to visualize without having like a drawing or a diagram, but the drag curve, what we refer to as a drag curve when we start talking about BCs and CDMs and PDMs. The drag curve is the coefficient of drag. It's like a plot, right? So it's like a graph, and you've got a line on the graph, and it's coefficient of drag and Mach number.
Okay.
So when your bullet has a coefficient of drag at a specific Mach number, and that table of values essentially is in the solver. It's either in the form of a BC, and we can get into kind of what that means as when we're representing a table of values with a singular BC number, or as a drag curve, which is a unique curve. Of a unique table of values, essentially. And that curve is, like I said, it's coefficient of drag to Mach number. So when you shoot, maybe you're at Mach 2.5. So that first time step in the solver is going to reference that table. Okay, it's at Mach 2.5, regardless of what the actual speed is.
Oh, yeah.
And it'll say at Mach 2.5, the drag coefficient is this. Plugs that into the equations. It's got your caliber, so your surface area. It solves the your aerodynamic drag equations, and can calculate more or less how much force is being put on the bullet to slow it down.
Yeah,
and it just keeps doing that in very fine increments all the way out.
How does Mach change with the temperature? How does that even happen?
It's just a physical property of the gas, right?
Is it just
air
because
is a gas,
the particles are further separated when it's hotter and they're closer and more densely?
Yeah, but without thinking of it, I don't want to answer the wrong way. But yeah,
Sure.
It really is. It's just how the particles of the air interact with each other at a different temperature. How quickly the more or less a shock wave, a sound wave, can travel through air.
Okay. Yeah. Now, everybody always talks about, when they talk about Mach, they talk about sound. And are they talking about sound just because sound is the, I guess, final product of what you get when particles are bumping into one another? I mean,
yeah. So
is sound actually more like, are they trying to say sound because you can actually hear it and that's how you perceive it, but it's actually like pressure or energy?
Exactly. So exactly what you just said. Sound is how we perceive that shock wave through air, right? But in relation to a bullet, what we care about is the shock waves and the drag that generates. So, I mean, what happens is the bullet's moving faster than the air can move out of the way of the bullet, and that generates shock waves on the profile of the bullet, a couple of them at various points. And the bullet is obviously moving through those shock waves faster than the shock waves propagate. So that's why you get like a cone of a shock wave coming off a bullet. So as the bullet passes you, you don't hear it until the shock wave gets to you.
Yes.
Kind of like that snap crack, right? Yeah.
Yeah, exactly.
I was even reading, I remember it, I found it interesting because they were talking about like how, jets fly through the air, and when they break the sound barrier and all that stuff, and the way that people were, especially when we first got into flying and breaking the sound barrier and stuff, they talked about the shape of jets, being real pointed and with those tight cone noses and real long and streamlined. And then they went into how, like, they started bringing back things from space, like capsules or whatever from space, and they realized that they actually couldn't make them pointed because the shockwave or whatever that was going around the pointed-nosed capsules when they were entering back into the atmosphere was heating up the capsule so much that it would just, like, deteriorate. And they actually had to make it, like, flat-nosed, so that way all of the energy went into heating up the air around the capsule and not the actual capsule itself. And I was thinking that was interesting because of like the shape of bullets and how fast bullets are going. That has to affect the bullet as well, I'd imagine.
Well, so when you're bringing somebody back from outer space or something back from outer space, your objective is to slow it down.
Sure.
So you want a lot of drag to slow it down and expend that energy into the atmosphere so that they don't run into the earth so fast that you can't recover it. We don't want bullets to slow down, so we keep trying to make them pointier and pointier until they slip through the air easier and easier.
Trying to make them more efficient at managing
exactly.
drag. Yeah. So I guess to bring that full circle, because I don't want to really leave listeners in the lurch on like one portion of what I've said about the ballistic solver. It cares about a few other things as well, being the target inputs, such as the range to the target itself. That's obviously an accurate range is going to obviously allow us to determine what the resulting drop is from the muzzle to the target. And then also the solver itself cares about gun profile inputs or the bullet inputs in particular. And that's a portion of why we're able to generate such or predict such accurate trajectories, using the line of AV software in whatever device the software is integrated into, is because the AB laboratory does all of that work in the background for the end user, establishing what the G1 and G7 BCs are, establishing what the custom drag model is, and developing and innovating the best ways to predict trajectory prediction downrange at extended long ranges. The last one being, we talked about environment as well. And within that, different inputs provide different features, such as, if you were to just run latitude in your ballistic solver, that would be accounting for horizontal Coriolis. Whereas if you were to run latitude and direction of fire, that would then give you your vertical Coriolis component as well. So there's things like that just allow the solver, or inputs like that just allow the solver to account for those second order effects. But in general, that's basically what we're trying to achieve. We're trying to give the solver really good bullet properties, so that the solver knows the shape of the bullet itself and how it performs in the relative air density, and how much drag that bullet's going to experience at whatever velocity it's doing relative to the speed of sound. And then we also want to know, where the target is, and what the wind is doing downrange, and what the environment is doing, or what the air density is. And that basically brings everything together holistically to give us the firing solution that should enable you to hit your target.
Questions like this might bring eye rolls to you guys, just because I'm sure you get asked these all the time. But you bring up phrases like Coriolis, which anybody who's watched like a sniper movie, they think like, oh yeah, Coriolis, man. If I know that vocabulary there, like I'm going to impress all my friends. I don't actually even know what it is, but like Coriolis, or you talk about aerodynamic jump and some of these other factors that you guys are considering in the equation that is happening under the hood that it's sort of figuring out for you. Like, what are these things?
So that's
some of
what
these interesting phenomena that happen to our bullet. Just even go through some of those.
So that's what Chris was referring to as second order effects.
Yeah.
So
okay. Yeah.
Your primary, what most people think about calculating a trajectory, you've got a bullet and it's moving through your 3 dimensions of space. So you got your 3 degrees of freedom. It's going downrange. It's got some left to right component, and obviously it's got lift and drop, mainly drop. And so, for instance, spin drift. So your bullet's spinning about its axis. The process of that taking place actually causes the bullet to veer off of its original path slightly. So that's spin drift.
Because there's friction between the surface of the bullet and the air, and it's almost like grabbing.
No, spin drift occurs because we're essentially creating rigidity around the bullet's spinning mass.
Yes.
And when you force the bullet to trace with a trajectory, it reacts by pointing its nose into a out of plane angle called the yaw of repose. So
it's spinning, and it's also trying to go like this while it's spinning.
You've got gravity pulling it down away from its spin axis, and so it reacts by pointing its nose slightly.
Yeah, I suppose you could probably, I guess I've never tried this, but you could probably almost get a feel for that if you try to spin a bike wheel or something really fast, and then as you try to move it, it resists your movement. That's kind of what's going on.
If it was like that, but I didn't want to sound stupid.
Yeah, so you have something
stupid enough.
You have to keep in mind, a bullet's suspended in midair, right, when it's flying. So anything like that, it has an effect, and so you've got your equal and opposite reactions, and it goes that direction.
So can I ask if this is, and I'm asking if this is an accurate analogy, but if you have a left-handed quarterback or a right-handed quarterback and they throw a pass, the ball will either curve to the left or the right. Is that,
you think?
I'm not sure.
That's not not necessarily spin drift. That's probably Magnus drift.
Yeah, with subsonic stuff like that, you get Magnus.
Yeah. Probably the coolest thing
I'm a big
I've
Magnus
seen.
drift guy, Jim.
Yeah.
Yeah. Probably the coolest thing I've seen on that is a YouTube video where some dude's just spinning a basketball off a bridge, and you can fully watch it curve as it flies down a valley.
Yep.
Yeah. As opposed to spin.
That's Magnus drift.
Yeah.
So
totally different.
Yeah.
Not even remotely close.
No, okay.
Yeah. So anyway, with spin drift, it's obviously related to how fast the bullet's spinning, its caliber, mass, all that good stuff, because that's kind of establishing the physics for what's going on. So with the right hand twist, it's going to veer to the right, and so that's something we have to account for in the solver. The other one we touched on is aerodynamic jump, and that actually occurs right at the muzzle. So as the bullet's coming out of the muzzle, if you have crosswind, the bullet coming into the wind, it
disturbs the bullet's spin axis.
It's a spin related.
So basically, like, I'll break it down to the shooter level for you, Mitch, because I know you're
I'm trying
to do
to
this
like
engineering thing, and
oh my gosh, we've broken him.
try and speak to the masses in shooter speak, right? So when the bullet exits the muzzle, it's kind of conducting some amount of pitching and yawing, right? Like up, down, left, right. And it exits the muzzle, and you have this crosswind. It might be like 10 miles per hour or whatever it is. Usually results in 9 or 10 miles per hour. Usually results in around 0.1 MRAD of AJ, right? So the bullet exits the muzzle, and it's trying to damp out the oscillations from being spun and launched out of the muzzle and fly point forward. But this wind just is cutting across your muzzle, and as that bullet exits the muzzle, it disturbs the bullet's spin axis slightly. And so as a result, like depending on whether the wind is coming from the left through to the right or the right through to the left will determine whether you have a vertical aerodynamic jump component high or low. So for a wind coming from the left, it would push the bullet low and to the right. Now, the right is a function of the wind deflection, not aerodynamic jump. Aerodynamic jump is just the vertical component, right?
Okay.
Now, for a wind from the right through to the left, that would push it, left and high. So that's just a very, very small, subtle component, but it's still something that we need to take into account nonetheless.
Does that change based on twist, like left hand or right hand?
It does. So it would be directions reversed for a left twist versus a right twist.
Okay, we're assuming right hand twist there. Okay,
yeah.
Got it. I can kind of picture that.
Yeah.
You guys can explain it, but I can kind of picture it after you saying that.
And the one thing I was going to say, one thing people need to keep in mind with aerodynamic jump is that it only occurs at the muzzle.
Yeah.
So if you're shooting from like inside a building or something where there is no wind at the muzzle of your gun, like the projectile is going to fly for 10 yards before it reaches any wind, then that kind of it eliminates the aerodynamic jump because you.
Oh, really?
Okay.
Yeah, as that bullet damps out, after the first 20 odd yards, at that point there's going to be some subtle disturbance to the bullet's spin axis, but at that point it's damped out those pitch and yaw oscillations that the disturbance is quite minimal compared to what it would be at the muzzle.
Interesting. Okay. Yeah. So the window you're shooting out of in this theoretical situation wouldn't become like a muzzle.
No.
The muzzle is the muzzle, and it's going to...
Like you said, it would still have an effect, but, to start, you're only talking 1 or 2 clicks, and then once it's at that point, it's sub
It's
1
gonna be
click,
hard
and
to
it's
see.
nothing we can account for anyway. So
Now that vertical deflection, whether it's high or low, is occurring because the pitch angle of the bullet itself is asymmetric, being it's pitching at a slightly increased or decreased angle, high or low, relative to the direction that it's been disturbed. And so it's that variation in pitch angle, high and low, depending on the direction of the wind, that causes the deflection that we see downrange.
Okay.
I mean, when you start talking about second order effects, it really comes down to the size of the target that you're shooting and how far you're shooting as well for it to really matter, Yeah.
And then, so the other one that I figured we'd talk about too was the Coriolis, right?
Yep.
And is that, all right, this is where just literally only Hollywood has taught me anything about Coriolis. It's where the bullet is flying and the earth is still spinning underneath it. Is that right?
That's pretty much it.
Hollywood, you did good. You did okay. You did okay. But I still, I kind of try to think about that. Like, I guess you were talking about if you know where you're pointed, the earth isn't always necessarily compared to where you're pointing going to be spinning in a perfect horizontal or perfectly vertical fashion to you. So it may be spinning at a slight angle or...
Yeah, so it's really just that. So when you shoot, the bullet's in midair, you're moving, the ground's moving, so that your target really isn't where it was when you shot. And so that's what you have to account for, technically speaking. And
but when you shoot and you're moving at the Earth's spinning velocity, when the bullet leaves the barrel, it would have also been moving at the Earth's spinning velocity too. So it's like it's the reason why when you're in your car and you like are going 65 miles an hour and you throw a water bottle up, it doesn't like fly to the back of the car, you know? So like, but it must obviously start slowing down the second it leaves the barrel.
Yeah,
right?
so it's no longer locked in with the ground spinning, right?
Got it.
So it's really all comes down to time of flight, right? So like all of these effects get magnified the longer the bullet's in the air. So inside 1,000 yards, guys hunting, say they're going to shoot an elk at 900 yards or whatever they're going to do, they're shooting at a big enough target, and you're still going to want to take into account, right? You're probably going to have a click of Coriolis. So maybe that hunting example is a bad example. But the average long-range shooter is probably shooting at targets big enough and close enough that if they ignored Coriolis, they're probably not going to see much of a difference in their capability to hit the targets that they're shooting.
You got to be a good enough shooter to distinguish, like, was I one click off because of Coriolis or me?
Yeah. But if you're trying to hit a prairie dog at 950 yards or 1,300 yards, then you better be factoring in Coriolis, because if you're a click off, then you're going to miss the prairie dog,
That's
right?
a couple prairie dogs.
So that's where, like what Chris was saying, that's where like Chris was saying, it really comes down to your target size and how far away it is, because it's all relative.
Sure.
What we're trying to hit. And we actually have a really great tool called WES. So we have a software that you download onto your desktop. It's called Applied Ballistics Analytics. And it has a tool built into it called WES, and it's called Weapon Employment Zone. And really what it does is it calculates your hit probability based on all of these inputs that we've touched on, but it's really looking at your error of these inputs, right?
Okay.
So I can read wind to within plus or minus 3 miles an hour. So you tell it that. You're like, okay, I can determine the temperature to within plus or minus 3 degrees. And my rifle shoots 1 MOA. So you plug in all those type of variables, and it'll actually run a simulation of like 1,000 shots, and it'll like overlay them over the size of the target. And it's like, okay, so on your first round impact, your first shot, you have a 3% chance of hitting that target, right? And it's pretty amazing when you start playing with that, just how difficult some shots are, and it really does match reality, because a lot of people say they hit stuff that when it comes to on game day they don't hit them.
It's got to be a bit humbling to.
Oh, it really is.
Because I mean, if I think to myself, like, what temperature do I think it is in here? I have no idea.
Yeah, which so
70.
Like you said, you
right.
had Katie in here with Kestrel, so we've got tools to measure those things, right? And those, if you're going to use that to get your atmospheric data, well, Kestrel has actual specifications for the accuracy of those sensors, right? So you can put that right into the WES analysis. And my point with that is, and the reason why I brought it up, when we're talking about aerodynamic jump and these second order effects that go into figuring out these long range shots, you can actually put in the size of your target and how far away it is and run your simulation, and you say, okay, if I totally ignore Coriolis, I still have a 65% chance of hitting this target, and if I factor it in, maybe I've got a 75% chance, right?
Yeah.
So you can start weighing whether or not these things are important, but it's kind of a moot point, because if you get WES and you start playing with that, you're probably at an advanced enough point where you're factoring in on all your shots anyway. Yeah. So it's one of those things that we kind of talk about the importance of it, but if someone's going to start shooting long range and they're going to get into it and they're going to buy some good scopes from you guys and all the tools to make it happen, you might as well learn how to do it right and just start factoring that stuff in right from the beginning, because even if when you begin it makes a half a click difference, well, now as you start to like push your limits, you're just going to be that much more capable and be able to shoot further. So it's one of those things you don't really want to take and learn half measures. Like, you might as well learn to do it right off the bat.
Yeah.
I think the thing is too with weapon employment zone analysis is it allows you to manage your expectations as well.
Yeah.
Because if I was to ask you, like, okay, we're going to get down behind this weapon system and everything's dialed in and everything, it's just going to come down to your ability to make a solid wind call, and we're going to shoot this target at a mile, first round. and you've got a solid indication or familiarity with what that weapon system is going to do for the cold bore point of impact shift from short range zero, and also the cold bore muzzle velocity for the first round or two, and how that's going to warm up. Even then, I'm like, well, you've got all of these factors that you're accounting for. What do you think your percentage or your probability of hit is on that target in some term, like in some amount of percentage? You're like, well, I don't know. Like that's right. Pretty hard, right? So what weapon employment zone analysis allows you to do is assign a hit percentage to that based on that 1,000 round first shot simulation. And that does allow you to manage your expectations in terms of, okay, I might have, a 20% hit probability on this target with my uncertainty parameters and my skills and abilities to hit that target. Now, that 20% may or may not be good enough for you to, warrant taking that shot. But it also allows you to determine, this is what I need to work on as a shooter as well. Yeah. Or, wow, it's really just my wind calls that are killing me, or, reducing my ability to effectively engage that target, in which case I can go away and work on my wind calls by, even just bringing the Kestrel with me when I walk the dog and just periodically checking the wind.
Yeah.
But, that's a great little tool to have. You just need to manage that honesty when it comes to inputting the uncertainty parameters as well.
Yeah.
Like if you get down on the range and you're only shooting sub 2 MOA, and to punch in sub 2 MOA inherent precision on the weapon employment zone analysis kind of hurts your ego a little bit. Like you're never going to have a realistic hit probability calculation. Right?
I'm sure there's also an element too of like, it might say that you have a 90% probability at 400 yards, but you're like, okay, but I'm also upside down on a rock and my neck is kinked. There's some of that too.
Yeah, and I mean,
the
easiest way to account for that once you become familiar with the program is actually just to manipulate your inherent precision, because that's not the inherent precision of just the weapon system itself. The weapon might group half an MOA or, even better, but if you're only capable of grouping 1 MOA, your precision capability is 1 MOA. If you're shooting alternate positions, maybe you can only get 2 MOA out of it, in which case you can just manipulate that input to calc your hit probability for that inherent precision.
And can you separate those things out? Like let's say let's say that Jim's a way better shooter than I am, right? And he can take that weapon system and he's got half MOA, right? And just bang, bang, bang. Yeah. And then I get behind it and I'm like, oh no, it's 1 MOA for me. You can separate those things out.
Yeah, you can run those. Cool. So basically you could sit there and from an alternate position or just from prone, whatever the scenario is where that precision or your grouping capability is changing within your own individual abilities, you can then also analyze, well, if I was able to shoot from a more stable alternate position, it would reduce my grouping capacity down to, half an MOA or 1 MOA or whatever, in which case that would increase my hit probability to this. So, and then, as you're saying, Mark, you can compare the hit probability shooter to shooter as well based on your abilities. So,
nice.
Yeah.
I don't know, man. Sounds like it could be kind of demoralizing. I'm going to go with the ignorance. The ignorance is bliss.
That's right. You guys have so many tools available, and one of the really cool ones, and actually we haven't really even fully dived into this one yet, but is the custom drag curves.
Yep.
And then also, I think that'll probably lead into the PDMs, which is personal drag models.
Yep.
But when you guys are making this custom drag curve, so you guys kind of took, there's the G1 and the G7 ballistic profiles, and that kind of assumes a general shape of a bullet. But obviously, when you talk about different grain weights of even within the same caliber, you've got different lengths which change things, and then you talk about obviously calibers, which changes the sectional density, or I don't know what I'm saying. But the size and shape of bullets, you're actually taking into account each individual bullet and determining how it will fly through the air. And so I'm curious about that, and then also how it is that then you've taken this custom drag model for 140 grain Hornady ELDX ammunition, right? But somehow that's even yet still a little bit different when it shoots out of my Ruger American Predator versus Mark's Weatherby whatever.
Yeah.
You know?
Yeah. So this is a conversation we've had a few times now on different platforms, and honestly, I think the best way to start is to kind of back all the way up to G1.
Okay.
So a G1 BC, kind of the old school number that everyone always used to use.
The OG.
The OG BC.
The OG
yeah.
G1, that's right.
So the G1 is or any BC for that matter, is it's a standard drag curve for a standard bullet. So there is a G1 standard bullet shape, and that is a very determined bullet shape. It's a very blunt nose with a flat base, and if you shoot that bullet and measure its drag curve, which is the drag coefficient at each Mach number, and that's where a lot of people I think have trouble visualizing it, is this drag curve.
Mm-hmm.
So I should get in the habit of carrying around an example of it.
Just a big fold out.
Just
in your pocket.
I can like fold it up and hold it up. Yeah. But it's so anyway, you've got this drag curve, and it's a very specific shape for that specific shape of bullet. Anytime you start to change the design of the bullet, where you change the MEPLA diameter, which is like the flat open tip or like the flat tip on a plastic tip bullet, like the Hornady's.
Okay.
Or you put like a boat tail on it or a flat base. You start changing that. The actual shape of the drag curve, which is the drag coefficient to Mach graph, that plot of values, that shape changes. So when you try to use a G1 BC, the reason why it was the one that always used to be used is because we had a lot of flat base bullets. They were relatively blunt because that's just how we could easily make them. We're talking early 1900s. And it made sense to use that because the G1 shape, the shape of the G1 curve really closely matched the shape that all these other bullets had within people's ability to tell the difference when they were
kind of like
calculating
one size
trajectories.
fits all.
Yeah,
Like when
and
you
because
buy a glove at the store, like it's made for people who have 5 fingers.
Exactly. So then when we started to do more trajectory calculations and we got bullets that started to have boat tails on them and they were getting longer and more pointed, we switched to the G7 because that was a better shape and there was less error. Because when you go back and you really look at people using G1s, you couldn't just use one G1 BC to get a good solution. You had to run what they called was banded BCs, where your calculator would actually allow you to put in different BCs for different velocities. And that's because that shape was enough different on the curve. You had to scale the G1 curve in different segments to kind of line up and force your trajectory to line up correctly.
In velocity bands, and that's a function of like when we're calculating ballistic coefficient, right? I would, start this by saying ballistic coefficient is a measure of how well a bullet penetrates the air or maintains velocity, right? For those listeners. But when we talk about calculating BCs, it's weight, cross-sectional area, and form factor. And form factor is the big one. That form factor is going to change, or the amount of drag that bullet experiences downrange is going to change relative to Mach number or velocity, right? And so we're using form factor, and I should say form factor is the amount of drag an individual bullet experiences compared to a standard. So you could have a G1 form factor and a G7 form factor. So to kind of, as an example, let's say that one bullet had a form factor of 1.1, and that would be 10% less efficient than the drag of the standard, G1 or G7, whatever form factor it was. Let's say we had another bullet that was 0.9. Well, that bullet would be 10% more efficient than the standard. Oh. So a lower number is actually better when it comes to form factor. So for the reason Mitch is talking about, where because we're going ahead and calculating a ballistic coefficient in parts with the form factor, because that form factor changes as that bullet's velocity changes, you have a large variation in form factor you have a large variation in G1 BC, especially when you're shooting a modern long-range bullet, because it isn't comparable to that G1 standard.
Yeah, and that's where it gets hard to visualize, because what the BC is effectively doing is scaling that drag coefficient to Mach curve up and down to try to match the actual drag of the bullet you're shooting. So the G1 has that specific shape, but it's not a very good match to the modern long-range bullets. So we had to scale that a lot. And because we're scaling it a lot and the shape's not very good, that's why we had to do it in different segments to try to get each part to kind of line up as you go from, Mach 3 or Mach 2.5, wherever your muzzle velocity is, all the way down through subsonic velocities if you're shooting long ways. So then we go to the G7, which is a much closer fit. So the shape of the curve and kind of the drag values that curve represents are much closer to what modern long-range bullets are. So when we started using G7s, we didn't need to run like a banded G7 BC because the errors in that curve were a lot less.
Okay.
But now we're getting bullets, like a lot of the Hornady A-tips, the Berger Elite Hunters, the EOLs, we're just getting such heavy, long bullets that a lot of them have error even from the G7, right? So that the way we correct that is we go to a CDM. And what a custom drag model is for that bullet, instead of trying to make this standard curve that is the G7 curve for the G7 shaped bullet, to scale it to fit this other bullet, we just measure that curve for that bullet. We kind of skip the middleman and just generate a new curve. And so that curve, the shape of that curve matches exactly the drag at each Mach number of that bullet. So that's what a custom drag model is. And what we do is we get bullets from every manufacturer. We go and buy them from, whatever store people buy bullets from, all the various ones, because we want to buy the actual
bullet store.
Well, yeah, I was going to name them, but we get them from like Midway USA and Brownells, and because we want to get actual examples of bullets that people are shooting, right? Like we're not going to the manufacturers and being like, send
not
us.
Like here's the really perfect ones.
Yeah, well, because we have this database that people use, and people reference that database to get BC numbers and kind of compare, right? So we want to make sure we're not getting some sort of like pre-production run that's slightly different than. So we just go and buy all the bullets, and then we test them, and we actually measure that curve. And the reason why, to kind of take a step back and explain why we didn't just do that in the first place, is until we have the equipment that we have now, like we started measuring with time of flight measurements, and then now we've gone to radar. But in the past, when it wasn't easy to do those things, getting that shape of that curve was very difficult. So once they had it established for the G1 and the G7, we've got most of the work. Now we just need to apply a factor to that to kind of shift it to get things to line up. So really, the advancements in the technology that we have available to us to make these measurements has made CDMs and now PDMs possible.
So I was going to ask, people must have thought you guys were crazy when you basically started saying, well, we're just going to figure out the BC for everything, exactly.
Yeah, it really,
people were like...
That's probably the way that people could understand it the most, is instead of calling it a CDM, you could almost call it like a G Hornady 110 A-tip BC, because it is for that bullet, right? That G7 is really for a specific bullet design. So the custom drag model is its own shape.
And when
it's
people
are
using your CDM, the BC is 1.00.
Correct.
Yeah, exactly.
Because the BC is
it's not scaling that curve at all.
Yeah.
So that's what a CDM is, and a PDM is essentially the exact same thing, but we're measuring it for your specific rifle.
Yeah.
And I say rifle, but it's for your barrel, your suppressor, your lot of bullets, all of that. Because what we've found, and we found a lot of this because we shoot a lot of ELR, right? So we're trying to shoot 2,000 yards, 2,500, 2 miles, and that's where all of this stuff gets exaggerated. You have to have the drag spot on. You have to have your velocity numbers spot on.
There's no it's close enough.
Exactly. So and that's where we've kind of learned a lot of this. But as we bring that down into, closer ranges, it just helps everyone hit smaller targets, right? So with a PDM and the tools we have now with our mobile lab, we go to these shooting events like competitions and some expos and other types of events, and where we can set up on a range and we can have guys come through and we set up the radar and you shoot 10 shots and we measure the velocities and the drag of those shots to as far as we possibly can at those venues, and we take that information. We've got all this computer code that we run it through, all the raw radar information, and it processes it, and it spits out. We still do the G7 BC numbers that way, because that's the one problem that I think a lot of people I don't want to say a problem that they have, but one thing with CDMs and PDMs is that you can't compare bullets that way, right? Because they're different things. You don't have a number where you can say this has a higher BC than this, because it's just different, right? So we still spit out G7 BCs. It gives you a starting point, and a lot of people still like to run G7 BCs. So what we'll do is we'll get a printout that gets them all their velocity information and their BCs for what they just shot. But then we also generate a CDM, which is a PDM in that example. And we push that to our library with a special designator so they can go find their bullet with their little PDM designator in parentheses that has their data. And getting back into the reason why we do that, so first of all, from lot to lot of a given bullet from whatever manufacturer, the BC can change, right? Because anytime they're setting up and they're taking down the dies that make these bullets, it's just not the same every time. Some manufacturers are better than others, but there are variations. So if we can't just keep our library up to date with every lot of bullets from every manufacturer. Like, that's just not feasible, because we've already got like 1,000 bullets in our library, and we try to keep them updated periodically, but we can't account for that. So you have lot-to-lot variations of a specific bullet. So, for one bullet, our CDM, when we test it, the G7 BC that goes with that bullet might be 0.285, but then somebody else gets another lot that it's 0.280, right? So you've already got a difference there from lot to lot of bullet. The next thing is different barrels, because that bullet is forcing its way down that barrel. It's kind of getting scratched up on the sides. In particular, when a barrel's got a high round count on it, it's got fire cracking, it's getting rough. It's actually really roughing up the side of that bullet, and now your bullet's got a lower BC than it did when the barrel was new.
Because it's just not as aerodynamically efficient when it's all roughed up.
Well, yeah, it's like you're just adding drag, right? You've got like the surface finish isn't as smooth.
All kinds of new surface areas.
Yeah, exactly.
In the round. Okay.
Yeah, so now you've got a barrel that's got 2,000 rounds on it, and your BC, or you've got more drag than what it was when it was new. So especially when we go to matches like this, guys can get this information right away, and then they can go and shoot a match with their most up-to-date drag information.
Oh, wow, yeah.
But so that's another thing. So you got lot-to-lot variation. You've got barrel-to-barrel, and that's just one barrel that's getting more worn, but from barrel to barrel, you just have differences. You could shoot the same lot of bullets in each one. You shoot 10 barrels, 9 out of the 10 are almost identical, but your 10th one, it's like, well, that one's got 3% more drag or less drag for whatever reason. And this is all stuff we're trying to like study and learn about, but it's you're starting to look at things that are just almost unexplainable, right? Until we have time to really break it down. So the best way we can manage it is to just try to measure people's drag for them through a PDM. And another thing too is launch dynamics, and that's we actually had an example of that when we had some of your guys out at your range shooting. And what that is when the bullet comes out of the muzzle, it's got more limit cycle yaw, which is the bullet kind of comes out doing something like that, more than it should, I guess I would say. And then as it starts to fly down range, it kind of dampens out and it starts to fly more straight.
Okay.
And so it's got more drag at the muzzle. And the problem with that is if you're not accounting for that, even if you have your muzzle velocity exactly correct and you're running what the BC for that bullet really would be downrange, you're still going to see an error, because for the first 20 yards, it had more drag than it did once it hit the 20-yard mark. So we were able to see that on the radar tracks for the one guy that was out at the range there, and we factored that into his PDM. And so now when he shoots that gun, it's got that factored in, and he doesn't have to worry about error from that.
How is the radar seen? Is it what kind of radar? What is it like?
It's so it's just like a scaled up lab radar essentially.
Okay.
It's
like a big giant rectangle thing.
Yep.
What is it? Is it shooting lasers out? I don't
No, it's Doppler waves. It's actual. They're like radio waves, and they go and they bounce off the back of the bullet.
Okay.
And we're measuring like the difference when it comes back.
How do man, now I'm getting into just the weeds. I'm sorry, but what are radio waves? Because I'm thinking to myself, like, okay, you got clearly it's not sonar, because sonar is sound and it wouldn't move fast enough to keep up with the bullet, right?
Yeah, no, they're just electromagnetic waves of
Okay.
a specific frequency, and
they can actually kind of like almost give you an image of the bullet as it's traveling down.
So
you can almost like
what
see
it's
it.
the only thing that it's measuring is velocity.
Okay.
So what it's it's going at a specific frequency out, a specific wavelength, I guess, to the bullet, and then when it bounces off the back of the bullet and comes back, it's slightly different, and it's measuring that difference, and that difference tells it how fast that projectile is moving.
Okay.
So it's taking those measurements at a specific frequency, and it's logging the data points of essentially how the velocity is changing as
How
it
can
goes
you
down
tell
range.
if a bullet is doing that kind of wavy yaw
Well,
and pitch
so
thing?
in
through
that
the-
example specifically, the way it manifests itself is in increased drag. Because if it's flying like this, it's presenting more surface area to its forward momentum or its forward trajectory, and it just has more drag. So what we'll see on the radar track is the bullet comes out and it has more drag at the muzzle, and then like the drag kind of drops quickly as it dampens out, and then the drag just kind of slowly increases as it slows down. Is
Okay.
just what a normal track looks like.
And you can detect how much drag you have by how much of like
by how quickly it's slowing down.
how much. Oh, okay.
So
oh,
we should,
got it.
caveat that or explain that by saying, that initial launch dynamic is causing some amount of velocity decay, and so that shooter is experiencing that bullet is slowing down faster than what it otherwise should if it didn't have an initial launch dynamic.
Yeah, which
so
would
in
mean
which
more
instance,
drag.
Yeah.
So in which instance, Mitch was kind of saying you could plug your muzzle velocity in from a good accurate chrono reading, and then go ahead and engage a target at longer range, and the firing solution may have some amount of error in it because you're suffering from that initial velocity decay at short range.
Yep.
Okay. Wow.
So those are the types of things that we can account for with the PDM that without taking careful measurements, you just wouldn't know with your system. And the reason we've gotten to this point is, like I said, with shooting ELR, but as guys have been shooting the data that we generate, and just over time we've noticed small errors where it's like, stuff's just, even though we've done everything right, stuff just wasn't lining up, and that's where we've started to catch on to these little differences. It's like, oh, the different lot of bullet has a different BC or has different drag, and this barrel's different than these barrels, or this barrel manufacturer is different than these barrels.
How do you know what lot your bullets came from? I don't know. If
It says right on the box.
Oh, it does.
Yeah.
Okay.
Yeah, so for if you're buying loaded ammo, you could go by the lot of the ammo. We're talking specifically the bullets themselves, because they're made in lots, which is typically with the bullet making dies are set up specifically, and they run tens of thousands of bullets, millions depending on the manufacturer.
And one kind of interesting thing I remember, Ruben was saying this when we were out there, because I was asking him, let's say you guys are out at a competition, somebody comes up to your guys' trailer, they get a PDM made for them. I was curious at first because I'm thinking to myself, okay, well, let's say they're in Colorado at high elevation and it's really hot out. And they get that PDM made for them, and then they head back to Timbuktu where it's a low elevation and not very hot out.
Yep.
The the PDM is actually that doesn't matter for it.
Nope. It's really just
Blows my mind.
It's the shape of the bullet. It doesn't. They say the shape and the initial limit cycle yaw and the surface finish of the bullet. All of that is what matters. The drag coefficient, which is the drag I'm mostly referring to on that drag coefficient versus Mach plot. The drag coefficient is independent of the atmospherics at the time.
Right.
So the Mach changes, and that's what would change. So it's not that I would go from this dramatic change in atmospherics and just have no changes in my dope. You would still have changes in your dope, but it's because of other things like the Mach has changed.
Well, I think the best way to explain it would be that when we're calculating drag coefficients, we're taking into account the atmospherics at the time, so that we're separating them. The atmospherics are an input into this equation, and so is the coefficient of drag.
Okay.
And we know what the atmospherics are before we test, right? Like we can measure with a Kestrel or some other weather station. Yep. And so we know what those are, but then once we shoot the bullet and we know the velocity decay, we can backtrack what the actual coefficient of drag is. And that's totally separate from the atmospheric. So you can take that coefficient of drag, which is that table of coefficient drag values and take that anywhere in the world with any atmospheric conditions, and then you plug those into the equation with the coefficient of drag, and you've still got a really good solution.
So you almost have like a constant, and then you're just adjusting your variables.
Yeah, it should be
Listen
a
to
constant.
that math,
Yep.
Jim.
Way to go. Nice. Man. My you guys have truly, like, this is like mind-blowing stuff. One other one that I've been like super curious about as well is people talk about going transonic.
Yep.
Oh, that was yes.
And so you have this aspect of, you know, a lot of the let's assume for now, but I want to also talk about subsonic ammunition and stuff like that. But anyway, let's assume we're talking about somebody who's shooting a round that will be traveling supersonic above Mach 1 to start. And then there's this period of time, and it could be at, you know, a certain distance. You may find that, I know the guys experienced this at Coon Rock, the range, where they were shooting at, you know, dead on at 1,000, right? Like boom, 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 super reliable, super predictable. You go out to, I think they even said like it was 1,050 or something, and all of a sudden, no idea what was going on. It was all over the place. And it's because, you know, at that certain point, for whatever reason, with that setup, they started going transonic, so switching between, because the bullet had slowed down enough, supersonic to subsonic. So why does that cause such an imbalance or something in flight of the bullet that it just creates this momentary, because it almost seems like it stables out again once it goes subsonic, but you guys may have other things to say about that. What is it about that region that's so crazy?
Really, we can categorize this into like talking transonic and subsonic effects. Transonic is going to start at about Mach 1.2, right? And those transonic, subsonic effects that you're going to potentially experience would occur all the way up until maybe 0.8 Mach. So basically, there's this period of time, or there's this Mach period that the bullet is essentially clearing the sound barrier and reaching that Mach 1 and then continuing through the sound barrier to subsonic, right? But the variation that you could potentially see downrange through trans and subsonic is, for the most part, relative to bullet design. Now, some bullets will transition the transonic flight regime a lot better than other bullet designs. In part, it can be a function of the bullet design boat tail in particular. And when we talk about bullets being inconsistent at extended long range, and I say extended long range because it's a good way to term the shooting beyond the supersonic into the trans and subsonic flight regime, right? And basically, when we are talking about clearing the trans and subsonic flight regime, we're kind of, it comes down to a few different factors, right? Like how capable is the bullet or the bullet designed to consistently clear that sound barrier without variations in drag or drag inconsistencies, which is where we would start to experience vertical dispersion. We're also interested in, especially at those ranges, what the BC standard deviation is, or the drag consistency from supersonic all the way into trans and subsonic, right? But I would say that, you know, when a bullet starts to become unstable or starts to tumble at trans and subsonic range, it's because of dynamic stability, not gyroscopic stability. So,
so it's not necessarily that it stops spinning enough.
No, it doesn't.
It's
still not spinning enough, but it's not spinning enough for that specific design. Because that's where, like Chris was talking about, where it's really design dependent. Some bullets will need to be spun way faster to make it through transonic unscathed, so to speak, versus others.
So the reason being that you could essentially, fire a bullet through a faster than generic twist rate, like for example, on my 308 Winchester comp guns that I'll use for various sniper competitions, I'm running a 1 in 9 on my custom built Applied Ballistics Weapons Division bolt gun, and a 1 in 8 twist on my Sons of Liberty Mark 10. So I run those excessively fast twist rates or faster than generic twist rates, because I know the individual bullet that I shoot, being the 175 OTM, performs really quite well for a 1 in 8 twist at trans and subsonic. Now, the caveat to that is, and what I'm really doing is I'm trying to reduce the bullet's limit cycle yaw.
And that's the bullet flying like this.
Sure. Yeah.
So by reducing the bullet's limit cycle yaw, I can kind of offset any dynamic instability issues through trans and subsonic. I know that bullet transitions through the sound barrier extremely well in general, but I can maximize my weapon's maximum effective range by spinning that bullet excessively fast and reducing that limit cycle yaw through trans and subsonic. If I'm not going to shoot that bullet into trans and sub, why twist it faster? All I've really done is increase my spin drift, right? Until you reach the transonic. Like really all you are doing is increasing your spin drift.
Yeah.
But through the trans and subsonic, there are benefits to be had there, but the main point being by increasing that gyroscopic stability, you're able to offset any dynamic instability through trans and sub.
And just to quickly touch on, so Chris touched on kind of like the practical side of how to like avoid those issues, but the actual mechanics of what's going on is the shock wave that the bullet is forming is more or less like catching up to and then starting to pass in front of the bullet. That transition, literally a transition, is where that instability occurs. It's very, I'd almost describe it as like a vulnerable point for the bullet. And if things aren't perfect, it can throw it out of whack and tumble.
The shock wave was almost before keeping the bullet stable in some ways. Is that correct? It's probably incorrect, but like as it transitions, it's just putting pressure on the bullet differently.
That's exactly right.
Okay.
Because
it's consistent for a while, and then it starts to become inconsistent before it becomes consistent.
And because the important thing to keep in mind is that again, the bullet's not flying perfectly straight like this. It's kind of doing this.
Sure.
And so when you've got the shock waves at various points on the bullet and it tips just right, if you got a shock wave over here, it can force it to tumble.
Yeah.
So that's kind of what can happen. And the reason why it's not just a definite line is because the air is actually accelerating around the bullet. So if as the bullet dips just below subsonic, so to speak, the air is having to move out and around the projectile. In that process, even though the bullet isn't going faster than the speed of sound, as the air has to accelerate to get around the bullet, like going around an airfoil, the air actually will reach Mach 1 and supersonic speeds. So you still get shockwave formation even though the bullet itself isn't going faster than the speed of sound. And that's why there's like a band of velocities that are known as the transonic range, where you kind of have these issues at play. So it's not one definite velocity.
You might be at 0.9 just because of how fast still at 0.9 the air is moving over
exactly.
It's
still not quite out of danger yet.
and then once it kind of goes back into full on, let's say below 0.8 or what, to throw out a number, once it goes back into subsonic, then now you don't have all this action happening.
You don't have any supersonic
flow.
You don't have any supersonic airflow around the projectile. It's just all subsonic flow at that point.
No supersonic flow, Mark.
Yeah.
Right?
Does this mean we're bringing the supersonics back? Is that what you're trying to tell me, Jim?
Always my favorite color scheme in the NBA.
Well, we'll see what happens.
Man. Okay, I was going to ask you guys, too. This is a stupid question, but it's one that like when I actually try to think about it and put a reason on it, I can't. But like in an ideal, I don't even like. Why do we spin bullets? Okay, so why do they need to have a spin on them? You know what I mean?
It's pretty simple. So like the little Nerf footballs that have the fins on it, or like an arrow. I guess an arrow would be more applicable for this podcast. What you have is the center of gravity is in front of the center of pressure, and the center of pressure is like the point where the drag of the projectile is really acting on the projectile.
Okay.
And that's a stable condition to be in. So that's why we put fins on things, right? To help them fly straight, because the center of pressure is back here. It's kind of like pulling on the bullet, whereas the projectile, and the center of gravity is got its all of its momentum trying to go down range, and that's keeping it point forward. With a bullet, you have your center of gravity back here, and your center of pressure is up in the nose.
Okay.
And so where the air is pushing on the bullet is in front of the center of gravity, and it naturally wants to flip around the other way.
Okay.
So when you spin it, it doesn't allow that to occur.
Oh,
So
for
you
the
have
same
to-
reason you were talking about, like when you spin the bike wheel and you try to like change where you're holding it, it's hard.
Exactly. So, you need a very specific number of RPMs for a bullet at a given velocity to not want to overturn.
Okay.
And that's that overturning force of the center of pressure and center of gravity. And as long as those conditions are met, it'll stay point forward.
And that's why if your barrel twist is too slow and you're shooting too heavy of a bullet, which is real long, then it's going to end up
bullet-shaped
tumbling
holes in the side of your
keyholing.
target. Yep.
Oh, that makes a ton of sense now.
Yep.
Huh.
That's why the 200s don't shoot out of my 300 wisdom.
It's funny you kind of say that because I come across some guys here and there and they're like, oh, this explains a lot. I've been scratching my head on these subsonic loads for, the last 6 months and they just keep keyholing sideways through the target. And I'm like,
Yeah.
got to increase that spin, that twist rate. So,
Interesting. Mark, you should ask him too about high FOC arrows.
Well, so
Are you in on the high FOC arrow thing? I don't know if you shoot it.
I'm not big into archery. I'm not totally sure what you're referring
There's
to.
a thing where people are talking about real heavy. You talk about.
I mean,
you shoot bows a lot.
I do. Eric is way more into the Ranch Fairy FOC land than I am. Right?
We'll make this like a 2-minute intermission.
But it did bring. We were kind of comparing arrows to bullets, right? And you're talking about the weight, I guess, of the bullet is more towards the rear.
Yep.
Where really probably on an arrow, it's actually even with just a standard broadhead, you have you got 100 grains up front plus an insert, and then now guys are putting weighted inserts, brass insert, whatever.
Basically making it really heavy out.
Making it really so your front of center, so you essentially have like a percentage of that weight in front of the center of your arrow, and I think ultimately, you're getting better or one of the benefits is better penetration.
Yeah.
So I wish we had Eric right now because he's like big FOC guy right now.
Big FOC guy.
Yeah, so aerodynamically speaking, the veins on your arrow is where your center of pressures, the drag on the veins is bringing your center of pressure back. The further that is behind the center of gravity, which the more weight you put in the front, the farther forward your center of gravity is, keeping that distance as far apart as possible is what's making a more stable arrow.
Mm.
Where with the bullet, it's the opposite way, right? So you have the longer of a bullet you make, so these super long, high BC bullets we've got nowadays, you're pushing that center of pressure further forward, but your center of gravity is further back.
Oh, you're making it harder.
It's harder and harder. Like the further forward that center of pressure is, you got to spin it faster and faster. That's why the bigger, heavier, longer bullet that you shoot, or I should say the longer and heavier bullet you shoot for a given caliber, you got to spin it faster because that center of pressure and center of gravity distance is greater.
My goodness. We need ballistics people to follow us around everywhere and answer all of our questions because it seems like they can. Mark, I've asked them a bazillion. I don't know if you had.
No, Jim, I'm glad you asked all these questions because honestly, like this stuff is so scientific. I actually didn't even know what questions I wanted to ask.
My only last one I was going to ask is, what caliber do you guys shoot a lot of and like shooting most of?
Yeah, so I've been mostly shooting ELR, to be honest. So I've got a 338 Enabler, which is a cartridge we developed, and I shoot 300 grain Burger hybrids at like 3,200 feet per second out of that thing. So it's it's like a 26-ish pound rifle, and but it's stupid high performance. So I mean that gun, I rarely shoot it inside of 1,000 yards, and mostly it's a mile plus. So I shoot that a lot, and then that's probably my favorite rifle just because it's so accurate and such high performance that it really pads your ego when you're shooting it inside. Like you shoot at 1,000 yards because you're like, oh, I think it's a 7-mile-an-hour wind. But the reality is it didn't matter if it was a 7-mile-an-hour wind or a 3-mile-an-hour wind because all I had to do was hold left edge of the target and I still hit. But yeah, so that's just what I've been shooting a lot of ELR.
You plug that one into the machine a lot then.
Yeah.
His hit percentage is just
get that affirmation.
Oh yeah, for sure.
Super high H.
It's like likes on Instagram.
Yeah.
Yeah, and then I'm starting to shoot the 375s a little bit more again, which is a even more hardcore ELR round. It's not quite as fun as the 338 just because there's a little bit more recoil. 338's actually a little bit cheaper to shoot, which is it's still super expensive
That's
to shoot.
saying something.
But yeah. But I've been shooting a little 6x47 Lapua quite a bit lately, and I'm finding that extremely fun. So I might start shooting some PRS matches and stuff like that pretty soon, just because it's a good time.
Right on. Chris, how about you?
I guess unlike Mitch, I don't really, I've spent a bit of time behind 50 cals and 375s and whatnot, and I don't really take pleasure in being hit by a bus every time I pull the trigger. Yep. So, probably the largest I like to go up to when I can choose is the 300 Norma Mag. Yep. That is just a great cartridge. There's some really great bullets out there, like the 215 and the 230 hybrids are just... and that thing hammers, and I like to say that it's more bark than bite. It's still very, very manageable, and that thing's just absolutely a pleasure to shoot. And, similar to the 338 Enabler, it's, kind of boosts your ego a little bit inside 1,000 with the efficiency of the bullet and the wind deflection that you're not going to see. I mean, it's not quite as good in terms of quality of ballistic merits compared to the 338 Enabler or whatever, but at the same time, it's still nice to shoot. And then aside from that, if I don't want to get rocked around at all, I don't want to rock my weld, I just go back to the 308 Winchester, because the old 308 Winchester is just good fun. I've spent many years behind it, and sometimes you don't even necessarily need a ballistic solver to calc the closer targets. You can just use the force and call it 1.9 mil and send it. Yeah.
Just easy. Sometimes it's nice to go back to a cartridge, one that has such history with our founding fathers. I mean, it fought some of the oldest wars. You can find them in museums.
Yeah.
You got to use a ramrod. 308.
I didn't tell you this, Jim, but Mucky's got me back on the 308.
Oh, come on.
What do you think I'm taking
I
on
actually
this?
have no issue with the 308 because I have my Browning BLRs in 308. So we do like to get around with the 308 shooters, though, that it's all antiquated now because the 6.5 Creedmoor is the prom king.
Yeah, right.
Now the 6 Creed. So we take the mobile lab to these matches, and everyone's shooting a 6mm of some variant, 6 Dasher, 6 BRA, 6 BR, 6 Creed, but everyone's shooting 6mm these days.
Yeah. It seems that way.
We're
trying to make the 30-06 great again.
We'll do.
Oh, there we go.
Yeah,
bring it back. Yeah,
we're gonna see if we could do it, but
hey,
then Ryan's kind of got us on the 7mm kick. So who knows?
Those are both uphill battles.
Well, you heard it here. Our hopes have been dashed.
Yeah, they've been dashed, Jim.
That's right.
But that one, the Enabler, I think that's a very fitting name to be as into long range shooting and the rifles that you guys are describing. You need an Enabler in your life.
Oh yeah,
that's right.
Yeah, it's fun, man. Like I said, 300 grain bullets are in the case of the 375. We're shooting like 407 grain bullets. It's like 130 grains of powder, and
wow,
it's a good time.
Yeah,
sounds like it.
You definitely do some good work with that.
Oh yeah, like I said, it's just a blast to shoot because you can. I mean, it's just so easy to hit stuff at really really far distances.
Yeah,
but
right on.
Yeah,
well,
I love it,
guys.
Amazing.
This has been absolutely. I actually can't believe how much we packed into this amount of time. Super cool.
Yeah, we actually got into more detail on a lot of stuff than we have in other podcasts. I think there'll be some people listening to it a couple times to try to
back that
sift
up
through.
Please do. And then for reference, for those listening out there who just get super curious, they've got more questions, want to learn more and stuff like that. Where's the best place for them to go?
Yeah, really, they should, if they go on our Applied Ballistics website, to our Applied Ballistics store or any of other dealers, if they really want to learn more, we've got a number of books, the Applied Ballistics series of books. We've got Applied Ballistics for long-range shooting, and a bunch of other ones that really go into detail. I say they go into detail, but they're worded in a way that really almost everyone can understand it. Like, if you take the time to read it, you might read it a couple times, but you can grasp it. Brian did a really good job writing those books in layman's terms, as he likes to put it. And so some of the stuff we talked about, if you're having a hard time visualizing it, there's diagrams and stuff in the book to really help you grasp what's being said. So I really recommend people get those books and read them if they want to either better understand what we talked about today or get into even more stuff. Any of the Applied Ballistics books are the way to go.
Right on.
I would
Awesome.
also say, there's Applied Ballistics Training Division.
Yep, that's
that's really the link that we established to provide the the practical takeaways for what we just really discussed to the end user and just facilitating placing more hits on target. So that's that might be more preferred for some shooters where they're not necessarily looking to get really deep into the science, but more so just establish, well, Chris, how do I hit my target? Just tell me what's the dial.
Yeah,
Right.
Yeah. Chris
That's
offers
fair, too.
training on all the Applied Ballistics stuff. So
That's cool. And how do they find you guys in the mobile trailer thing? The
we've got
mobile
we've got a schedule up on our website. Things have gotten really shaken up with 2020 and
That's fair.
COVID, and we're pretty sure we've got a couple more events that have been canceled or are going to be canceled. So things are continually changing. But yeah, on the Applied Ballistics website, we're trying to keep a schedule up to date with where we're going. But if there's any match directors or anybody holding events, mostly we've been going to shooting events, but that doesn't necessarily reach hunters as much. So if there's anybody listening that has more hunting related events that they think they'll have a decent turnout of long range hunters, we're open to hearing about them and possibly going to those events. So if anybody knows of events that they would like to get data like this done, reach out to marketing@appliedballisticsllc.com. And, just reach out and say, hey, we've got this event, or I know of this event, and, we'll talk to them. And if it's a good fit, we might be able to make something work. But other than that, just pay attention to the schedule on our website and see if there's something nearby.
That's cool.
Very
awesome.
cool.
Yeah, thank you guys a ton. Really
Truly
appreciate
fascinating.
It.
Yeah.
Thanks
for having
everybody
us
for
on.
listening, as usual, as well. And, we'll catch everybody next time.
Thank you.
Bye.
Thank you.
All right, that'll wrap it up for this episode of the Vortex Nation podcast. Thanks, everybody, for listening. Hit that subscribe button so you can always stay up to date on the latest happenings over here at the Vortex Nation podcast. You can also follow us on Instagram at Vortex Nation Podcast. Again, everybody, thanks, and happy hunting and shooting. We appreciate it. Have a good one.